All right. Hi, everyone. Welcome to another class of 412. I'm going to briefly unmute you all so you can all say hi. Hey, everybody.
Hi.
Hi.
Hello. Hi.
Hey.
Hello.
All right. So I want to continue our series of lectures on profit maximization using digital goods auctions as a useful test bed for a number of new techniques. And let's just sort of take a moment before we begin to remember what we've done so far in this setting. So we started giving sort of auctions of the most classical type. We had all of the bidders show up. We knew quite a bit about them. We knew the distributions from which they were drawn, and we derived Bayes optimal auctions. We derived the sort of unique dominant strategy truthful mechanism that maximize expected revenue over whatever distribution of bidders we were given, period. And then we observed that auctions of this sort were impractical for a number of reasons. Maybe one, why is it that we can assume that we know all of the details about bidder distributions up front when we're designing the auction? It's not clear that we would know that. And second, that it's not clear we could even run an auction. In many settings, we can't gather everyone up front, and that led us to think about two kinds of relaxations. First, we sort of thought about pricing schemes. So first, we assumed maybe that we still knew the distribution from which bidders were drawn, but we derived pricing schemes that would allow us to still approximate the revenue of the optimal auction, but now without the need to gather everyone up front. We could just sort of put a price tag on the item, and people could show up one at a time and buy the item when they arrived. And then we considered the other relaxation. We considered these sort of prior-free mechanisms that wouldn't need to know anything about the instance. They wouldn't need to know the distribution from which bidders were drawn. In fact, maybe there wouldn't even need to be a distribution. And we talked a lot about revenue benchmarks. We sort of decided that at least for digital goods auctions, the revenue of the best fixed price was an extremely strong benchmark. And we showed how to achieve that first in an auction setting using the random sampling technique. And then last class, in an online auction setting. So in the online auction setting, bidders could arrive one at a time. We didn't need to gather them up front. We didn't need to know anything about where they came from. And we could allocate goods without knowing who was going to come in the future. And we still gave a sort of strong approximation to our revenue. We approximated the revenue of the best fixed price in hindsight. But what we gave last class still had to be called an online auction. It wasn't quite a pricing scheme. And the reason it was an auction rather than a pricing scheme is because we had this slightly awkward thing where even though our auction kind of looked like a pricing under the hood, like even though the way our auction worked is every day we used the multiplicative weights algorithm, the polynomial weights algorithm, to come up with a price for the good every day, and we were going to sell the item at the price we came up with using a take it or leave it kind of mechanism to the next bidder who showed up. Like, despite that fact, we actually required that the bidders had to report their valuations to us. That is, the allocation rule looked like a pricing scheme in that if your valuation was above the fixed price, you would get the item at that price, otherwise you wouldn't. But we didn't, like we actually needed the feedback where we needed to ask the bidders to report their true valuation rather than just showing them what the price was. And that was okay, as far as it went, because it still corresponds to a dominant strategy truthful mechanism. But it's, not super practical. It's not super realistic. Usually you don't see things sold using online auctions, you see things sold using pricing schemes, right? Like when you walk into the grocery store looking for, flour or hand sanitizer, it's not that the grocer asks you, how much is flour worth to you. Instead, there's just a price tag. And there's a number of good reasons for that. First, you might not trust the grocer, right? Like you might think that even if the grocer sort of promises you that they've got some price in mind and they're just going to tell you whether your reported value is above or below the price, that maybe that's not really what they're doing. And second, like that would just be complicated. It would complicate self-checkout and all sorts of things. And so it would be much more practical and realistic if we could do something similar, but instead of running an online auction, we used an honest to good pricing rule. That is, we just every day came up with a fixed price for the item, just as we did last class. The only difference would be in the feedback. We would only get to observe whether the buyer who showed up bought the item or not, and we wouldn't get to observe their actual valuation. And the reason we didn't do that last time is because it sort of corresponds to a more difficult learning problem. So remember the approach we took last time to trying to maximize our revenue in these online auctions. We sort of reduced the problem to a learning problem. And in particular, we reduced it to this experts problem, this online learning problem that we had solved way back when at the beginning of the semester, before the global pandemic. All sorts of things were different back then. And we sort of said, okay, well, each price is an expert. We can associate with each price the revenue that we would have obtained had we used that price. And then the guarantee of the polynomial weights algorithm was sort of exactly what we wanted, right? Like the guarantee of the polynomial weights algorithm was that we would do nearly as well as the best expert in hindsight, which in this setting would correspond to obtaining revenue that was nearly as good as the best fixed price in hindsight, the thing that we wanted to do. But the problem was that the setting in which we derived the guarantee of the polynomial weights algorithm needed quite a bit of feedback. In particular, it needed to be told at every round what the reward of each expert was, which corresponds to needing to be told in a pricing setting how much money we would have made counterfactually for every price we could have set, not just for the price we did set. And that's the kind of feedback that we could easily give it in an online auction setting when the bidder reported to us their valuation, because once we know the valuation of the bidder, we can figure out counterfactually how much money we would have made at different prices. The problem is if we only post a price, if we don't ask their valuation, well, we can figure out how much money we actually made given the price that we set, but we can't necessarily figure out all of these counterfactuals, right? Like if I set a price of $10 and the item is purchased, I actually cannot easily figure out what would have happened had I set a price of $11, right? Because two different things could have happened and I don't have enough information to disambiguate them. It could have been that if I had set the price at $11, I would have made $11, or it could have been that I would have made $0 because maybe, you're willing to pay $10 for a pound of flour, but not $11. And so that's sort of the difficulty. And it's the problem that I want to try to overcome in this lecture. So in particular, we're going to solve basically just a learning problem in this lecture and this learning problem will sort of immediately give us a solution to the dynamic pricing problem that we sort of really want to solve, this problem of dynamically setting prices to maximize our revenue. And the reduction between the pricing problem and the learning problem will be very similar to the reduction we saw last time, except now in the pricing problem, we get much more limited feedback. We observe the amount of money we make for the price that we set, but we don't necessarily get to observe these counterfactuals, the amount of money that we would have made at other prices. And so we'll need to solve a harder learning problem in which maybe there will still be experts, but when we pick an expert, we get to observe the reward of that expert, but not the reward of the other experts. Okay, and it sort of makes sense that if we can solve the same kind of online learning problem in this more restricted feedback setting, meaning, if we can come up with an algorithm for choosing experts that will continue to guarantee that we do nearly as well as the best expert, but if our algorithm now only requires this more limited kind of feedback, then we should be able to maximize revenue using a pricing scheme instead of an online auction scheme, because similarly, the only real difference between an online auction of the sort that we studied last time and a pricing scheme is the feedback that we get, right? We get more limited feedback in a pricing scheme because we get to observe whether the item was purchased at this price, but we don't get to observe what would have happened at other prices. Okay. And we will make, just to sort of make the problem a little simpler, we will make one simplifying assumption, not a terrible one. But in the last couple of lectures, we've assumed literally nothing about where the buyers come from. They could have been chosen by an adversary. To make things a little bit simpler for us here, we're going to go back to assuming that the buyers do have their valuations drawn from some distribution, but we don't know what the distribution is. Okay, so we're still going to assume that we as the algorithm designer, we as the mechanism designer have no knowledge of the distribution from which bidders are drawn, but we are going to assume that there is some such distribution, and our strategy, our algorithm design strategy will correspond to trying to learn things about that distribution. And I do want to remark that this assumption is not necessary. In fact, we can prove exactly the same theorems without needing to make this assumption that buyers are drawn from a distribution. The buyers can be selected by an adversary just as they were last lecture, and all of the theorems we're going to prove today are still going to be true. It's just that the algorithms we would need to achieve those theorems are a little bit more complicated, and we're going to solve the simpler problem just to get a flavor of the kind of learning problem that suffices to solve this revenue maximization problem from pricing. Okay. So what do we want to do? Rather than having an auction in which we elicit people's valuations directly, we want to come up with some dynamic pricing scheme. Okay, so what we get to do is sequentially, as bidders arrive, we get to offer fixed prices. So before the next buyer arrives, I get to slap some price sticker on the item that I'm selling. The buyer's going to show up. They're going to, look at the item. They're going to look at the price, and then they will buy it or they will not. Okay, so I don't get to observe what the buyer's valuation is. I only get to observe whether they bought the item or not, which corresponds to whether their valuation was above the price that I set or below it. And remember that although I said we're going to assume that buyers' valuations are drawn from some distribution, we as the algorithm have no idea what it is. So initially we know nothing about the instance, but as we set prices and observe what happens, we learn about the instance. So we get to learn about what's going on as we go. And as we learn, we get to change the prices. So it's a dynamic pricing scheme because the price that I set at day t can be different than the price that I set at day t-1, and it can be in principle some arbitrary function of the behavior that I've observed up through day t. Okay, so a little bit more formally, in the dynamic pricing setting that we're going to study, there are n buyers, okay? And each of them has some valuation. Like just like last lecture, we're going to normalize these valuations to be numbers between 0 and 1. And here's the assumption we're going to make here, which again is weaker than the assumptions we made when we designed revenue optimal auctions and pricings. We're assuming that the valuations are drawn from a distribution, but we are not assuming that we know the distribution. Okay. And so our goal is going to be to design the algorithm for the seller. And what the seller gets to do is sequentially at each time t, the seller gets to set some price. And again, because values are normalized to lie between 0 and 1, without loss of generality, the prices can also be set between 0 and 1. There's no point in setting a price larger than 1. You know for sure nobody would buy at that price. And buyers arrive one at a time. So on day t, after the seller has set the price, a new buyer arrives with their valuation freshly drawn from the distribution. And if their valuation is larger than the price, if they value the flower at more than it costs, they will buy the good. The seller will get revenue PT, and they will learn something. In particular, they learn that whatever the buyer's valuation was, it must have been at least as large as the price. Otherwise, the buyer will walk away. They won't buy the good. The seller will get revenue 0. And again, the seller will learn something. They will learn that whatever the valuation was, it was less than the price. Okay, so it's sort of like an online auction, except in an impoverished feedback model, right? In an online auction, you would learn after every step exactly what the buyer's valuation was. Here, you only learn a single bit of information. Was the buyer's valuation bigger than your price, or was it smaller than your price? So maybe before we go and think about algorithm design, this is a good place to stop and ask if there are any questions about the model, because we've now sort of laid out the rules of the game. You know, we've defined what a dynamic pricing scheme is, and we're going to want to now think about how to come up with one that can make sort of an optimal amount of money. So are there any questions about the setting in which we're working?
Just to confirm, everyone has the same distribution?
Yeah, that's right. So there's no distinction between buyers. Everyone's valuation is drawn IID from the same distribution. And to sort of reiterate, that's going to be very useful for the algorithm we design, but if we were willing to spend more time and design a more complicated algorithm, that's not a crucial assumption in this setting. We could still solve the problem even if the values were drawn by an adversary.
Got it, thanks.
Mm-hmm. Good question. Okay. So let's sort of remember our benchmark, which I'll write out again in this setting. So what we've been wanting to do is to compete with the best fixed price. Right? And that's actually sort of the same as the Bayes optimal benchmark if we know the distribution, because the Meyerson optimal auction would have set a, just basically a fixed reserve price in this setting. So the revenue optimal auction, if we knew the distribution, would just charge some fixed price. What that price is would depend on the distribution. It would be the inverse value of the virtual value function evaluated at 0. That's not something we know. But if we can say that we get as much revenue as the best fixed price, whatever that is, that'll be at least as good as the revenue optimal auction that we could have run had we known the distribution and had we gathered everyone up front. And so in this case, since we do have a distribution, we can write out what that benchmark is. So first, let's remember what our expected revenue is for setting some price P. And if we set some price P, then, well, if the item is purchased, we get P dollars, otherwise we get nothing. And it's purchased exactly when the valuation of the bidder is greater than the price. So our expected revenue for setting a price P is just the price P times the probability that a bidder's valuation is greater than the price. Okay, so this is the expected revenue from a single bidder if we set price P. There are n bidders, they're all drawn from the same distribution. So our expected overall revenue, had we set price P every single day, would just be our expected revenue for a single bidder times n, because expectations are linear. And our benchmark is just going to be the maximum revenue that we could obtain using any fixed price P. Okay, we'll call that opt. We would like to make as much money as opt. So our approach last time was to reduce this problem to some online learning problem where we would identify prices with experts and solve it using an online learning algorithm that had a regret guarantee, right? That guaranteed that we would do nearly as well as the best expert, and again, sort of identifying the rewards of the experts with the revenue of the auction led us to conclude that the auction that we designed had revenue that was nearly as good as that of the best fixed price in hindsight. And so we're going to try to do morally the exact same thing in this lecture. We want to reduce our dynamic pricing problem to a purely learning theoretic problem. Okay, now a harder learning problem because we have only this restricted feedback, and we want to solve this learning problem and then hopefully use the solution that we come up with to relatively directly come up with a dynamic pricing scheme that does what we want. Okay, and the family of sort of restricted feedback, censored feedback learning problems that we want to solve are called, for obscure reasons, bandit problems. So so first, like, why are they called bandit problems? And then let me tell you what the class of problems is. So slot machines are called one-armed bandits by a certain demographic. And you could imagine a multi-armed bandit problem that would sort of correspond to having a bunch of slot machines lined up, one next to the other. And you could imagine that each of these slot machines has some distribution over rewards, right? Like for each slot machine, when you pull the arm, there's some chance that you win some huge payout. Maybe like the lights start flashing and sirens start ringing, and you win like $1 million or something. There's some chance that you get nothing. There's some chance you get something smaller, and maybe each of these slot machines has a different distribution over rewards. And the idea is, okay, you're some guy sitting in front of this like bank of slot machines. What you get to do is you just get to play them. You get to put a quarter in and pull one of the arms and see what happens. And if you knew ahead of time which was the slot machine that had the highest expected value, you would just play that one every single time. But if you don't, then you have to do some experimentation. You've got to put the quarters in different machines. You've got to pull the different arms, and maybe make as much money as you could have had you known ahead of time which was the best slot machine. Okay, so that's sort of the metaphor and why this class of problems is called bandit problems. And the defining thing of a bandit problem is that when I pull the arm of a slot machine, I see the reward for that machine, right? I get some payout, but I don't get to observe the counterfactual, which is how much money I would have gotten had I put my quarter in another machine. Okay, so that's the background behind the name, and also why the choices that we have to make in this setting are traditionally called arms. But arms are really the same thing as experts. Okay, like bandit problems are really just expert learning problems where we get sort of a more limited form of feedback. Okay, so just to pin down the definition of the class of problems we want to solve, a multi-arm bandit problem is defined by k arms. Okay, but again, if you want, you could think about these as experts. And the variant of the problem we're going to think about in this class, so these are stochastic multi-arm bandit problems. And in that case, each of the arms is associated with some unknown payoff distribution over rewards that are just numbers between 0 and 1. Okay? Now, so every arm is associated with some unknown distribution over payouts, and it's got some unknown mean. Okay? And the idea is what the algorithm gets to do sequentially in rounds is choose an arm to pull, choose an expert to follow. And when it does so, when I pull some arm IT on day T, what I get to do is I get to observe a single reward. I get to observe the reward for the arm that I pulled, which is drawn independently from the distribution corresponding to the arm that I pulled, and that's it. I don't get to observe anything else. Okay, so it's like the experts problem where I've got these k experts. Every day the experts observe some, every day the experts experience some reward. I have to choose an expert and I experience the reward that the expert experiences, except in the standard, the way we sort of defined the experts problem, at the end of the day, the algorithm learns what the reward of every single expert is. Here, the algorithm only learns the reward of the expert that it chose. Okay? And then additionally, we're assuming here that the rewards of these experts are actually drawn from a set of unknown distributions, but you could define an adversarial version of this where the rewards are arbitrary. Okay. And just as before, we can talk about regret. Okay, so the algorithm, think about the algorithm as experiencing the reward of the arm that it chose. Okay, so if at every day, if every day T, I chose some reward IT, then I can write down what my expected reward was after T days. It's just the sum over all of the days of the mean reward of the arm that I pulled on each of the days. Okay. And I can write down what the regret of my choices were, right? Because in particular, I know I can sort of define in this instance what the best arm in hindsight is. Since the rewards are drawn from a distribution, I actually, I don't need the power of hindsight. I can know just what is the best arm. What is the arm with the highest expected reward? The arm that maximizes its mean. Okay, let's call that arm I star. The best sort of expected payoff that I could get with the benefit of knowing what these distributions are would be to just pull the best arm every single day. Okay, so the optimal reward in this setting, the optimal expected reward, is just T, the number of days, times the mean reward of the highest reward arm. Okay, this is T times the expected reward of the best arm. This is the reward of the best arm, in hindsight. It's the best I could have done. Now, my algorithm didn't have the benefit of knowing what these distributions were ahead of time. So it can't just play the best arm every day. It doesn't know what the best arm is. So my algorithm did something else. My algorithm played some sequence of arms that had some sequence of expected rewards that was only lower than the optimal expected reward. And my regret is just the difference between these two things. Okay, like if my algorithm somehow magically knew what was the best arm in hindsight, it could have done exactly the same thing as the optimal algorithm. It could have pulled the best arm every day. My regret would have been 0. If it doesn't do that, my regret will be non-zero, but the goal is to come up with an algorithm that causes the regret to grow relatively slowly as a function of T. So I'm going to want the same kind of property that I had in this expert setting, where I had sort of a richer form of feedback, where this regret function should grow sublinearly in T. So at least on average, as T grows large, I should do as well as the best arm in hindsight. Okay, does that make sense? And so let's think about how to do this, right? And maybe let's just think about in these bandit problems, what's really the defining characteristic of these problems? And if you think about it for a little bit, the thing that you really need to figure out how to manage in a learning problem like this is how to trade off what are known as exploration and exploitation. Okay, so here you are in the middle of playing this game. You've pulled all of the arms, some number of times. So you have like some evidence of what the mean payoff is for each arm, like in the form of the empirical rewards you've observed so far. So on the one hand, if you're going to do well, if you're going to sort of be able to compete with the expected reward that you could have gotten had you known ahead of time what was the best arm to pull, at some point you're going to have to exploit the information that you've gathered. Like at some point you're going to have to say, okay, like I'm pretty sure that like arm 5 is the best arm, and so I'm going to pull arm 5 because I want to get high reward. That's the only way I'm going to get low regret. On the other hand, you don't want to make decisions like that prematurely before you've gathered enough evidence, right? Because like suppose I've only pulled arm 5 a handful of times, then it might look to me that arm 5 actually has low regret. Right? It might look to me that arm 5 has low reward, not because arm 5 really does have low reward, but just because, on the handful of times I pulled it, I got unlucky. Okay? And so if I prematurely wrote off arm 5 because it appeared to have this low average reward and just sort of myopically pulled the thing that seemed to have highest reward, then I might never discover my mistake, right? I might never discover that arm 5 actually was the best arm. I just got unlucky the first 3 times I pulled it. And so there's this need to balance exploiting the knowledge you have with the need to explore, with the need to try things that you haven't tried often enough in order to gather more evidence. Okay, and so thinking about how to optimize regret is really sort of the question of how to best trade off the need to explore with the need to exploit the information you've gathered. And there's a number of ways to do this. Some trade off exploration and exploitation sort of more explicitly, like you could flip a coin and decide whether today I'm going to pull the arm that looks the best to me, or instead maybe I'll pull a random arm today. But there's a sort of very elegant class of algorithms that sort of optimally trade off exploration and exploitation automatically. And the philosophy they use, right, so the guiding design principle behind this class of algorithms is called optimism in the face of uncertainty. Okay, like optimism in the face of uncertainty somehow is a good idea in problems like this. And so what does that mean? Like what does it mean to be optimistic in the face of uncertainty? So what we're going to try to do is to quantify our uncertainty. Okay, so we're going to, at any given moment, have some empirical estimate of the mean for each arm. That'll just be the average of the rewards we've observed for each arm. Okay, so we have some empirical estimate for the mean of each arm, but of course, we're not certain what the mean of each arm is. In fact, if I've only pulled arm 5, like 3 times, then I have quite a bit of uncertainty. I don't have much faith at all in the empirical estimate. And so we're going to explicitly quantify our uncertainty by not just maintaining empirical estimates of these means, but by sort of explicitly maintaining confidence intervals around our estimates. And the algorithm design philosophy, optimism in the face of uncertainty, means the following. Like, we will always be as optimistic as we reasonably can, meaning we will assume that the arm's means, the means of these different distributions, are as high as they can possibly be in a way that is consistent with the evidence. Meaning we will assume that the arm's means are not outside of our confidence intervals. That would be inconsistent with the evidence. But we will assume that each arm has a payoff mean that is all the way at the top of its confidence interval. Okay? And then we'll sort of behave greedily, not with respect to the empirical means of the arms. That would be a bad idea because, if I got unlucky early on, and I only took 3 samples from arm 5 and they were bad samples, the behaving greedily with respect to these empirical estimates would lead me astray. Instead, what I'm going to do is I'm going to behave greedily with respect to my optimistic estimates. I'm going to every day pull the arm that has the highest upper confidence bound. Okay, so the reason this is called optimism in the face of uncertainty is we get to imagine that each arm is as good as it could possibly be, consistent with the evidence, and we play the arm that is best in this optimistic world. And the reason this is a good idea, and we'll do the analysis, to quantify precisely what our regret bounds are, but the reason this is a good idea is because there's sort of a win-win phenomenon going on here, right? Like if I pull the arm with the highest upper confidence bound, there's sort of 2 reasons I could have pulled it. Either the arm truly had high mean. Okay, like maybe the upper confidence bound was really high because the actual mean of this arm is really high, in which case that's great. Like I don't suffer much regret. Or, like maybe I actually suffer a great deal of regret today, like the mean of the arm was really low. But if the mean of the arm was really low and the upper confidence bound was really high, that means that I actually had a great deal of uncertainty about the arm that I just pulled. And so I gained something. I didn't gain reward directly, but I significantly reduced my uncertainty about the instance because I played an arm about which I had significant uncertainty, and I reduced that uncertainty. And so that's sort of the idea. That's why optimism in the face of uncertainty is going to work, because morally at least, there's 2 reasons I could have pulled an arm. Either the arm was good or the arm had high uncertainty, and something good happens for the algorithm in either case. Either it gets a high reward or it substantially reduces its uncertainty about the estimate. Okay. And let me just sort of pull one mathematical fact out of a hat for you. This is actually an extremely useful inequality if you're doing, theoretical computer science or analyzing randomized algorithms. So, if you haven't seen it before, you might want to remember it. And it's actually not so hard to prove. If we had another 15 minutes, 10 minutes, we could prove this. But it's a pretty simple statement. And you can think of it as sort of a quantitative version of the law of large numbers. Okay, so what's it saying? Like imagine we were gonna flip coins. Okay, so imagine I was gonna flip a coin 100 times and count the number of heads that appeared. Well, we know that if I flip a coin 100 times, the expected number of heads that would show up would be 50. Okay, but I would be unlikely to observe exactly 50 heads. So the question is, okay, should I be surprised if I see 40 heads? Should I be surprised if I see 30 heads? At what point should I start being surprised? And in general, if you ask the question, if I flip a coin n times, what fraction of the time should I see a heads? Well, like we know that as n goes to infinity, the fraction of times that I see a heads is probably going to go to 50%. And what this thing tells you, the sort of the Chernoff-Hufting bound, is a quantitative version of that statement. It tells you as a function of the number of coins you flip, at what point you should start to be suspicious if the number of heads that you see deviates substantially from the expected number of heads. Okay, so let's sort of read it out loud because it's slightly more general than what I just said. It applies to arbitrary distributions over numbers between 0 and 1. It doesn't have to be coin flips. Okay, so in fact, it's even more general than this, but this is the version we're going to use. And whatever this distribution is, it's got some mean. Okay, some mean mu. And so suppose that I take n independent samples from this distribution. Then I could come up with some empirical estimate for the mean. It would just be the average of these n samples. The question is, how far is the empirical estimate likely to be from the true mean? Okay, so this quantity here is the sort of the error term. What is the difference between my empirical estimate of the mean and the true mean? Okay, this absolute value difference. This is the error of my empirical estimate compared to what it's trying to really estimate, which is the true mean of this distribution. And what the Chernoff bound tells us is that for any confidence level 1 minus delta that we care to talk about, so if I want, for example, a 95% confidence interval, I would set delta to be 0.05, 5%. If I wanted a 99% confidence interval, I would set delta to be 0.01, 1%. What this is saying is that with high probability, with probability 1 minus delta, my empirical mean will be close to my true mean, the thing I'm trying to estimate, where close means it will be within this expression, something that looks like 1 over square root of n. Okay, so it's saying that my error, right, my deviation from the true mean with probability 1 minus delta will be something on the order of the square root of the log of 2 over delta divided by 2n. Okay, so this is going to 0 as n grows large. So this is recovering for us the statement that says, if we flip n coins, as n goes to infinity, I should expect that my empirical mean should converge exactly to my true mean. But it's giving us a rate. It's saying, actually, okay, I didn't have to flip infinitely many coins. If I flipped n coins, then I can quantify this gap, and it's something that sort of goes to 0 at the rate of 1 over the square root of n. Okay, so what the Chernoff bound is allowing us to do is it's allowing us to attach confidence intervals. It's allowing us to attach confidence intervals to empirical estimates of means. Okay, like just sort of saying this another way. Suppose I've taken n samples from this distribution. Okay, and I've got my empirical mean. Maybe I don't know what mu is. Okay. Then I can be pretty confident, I can be certain that with probability 1 minus delta, whatever the true mean is, it's equal to my empirical mean plus or minus this error term. Okay, and that's how it's going to be useful for us. Typically, we don't know what the true mean is. Okay, we want to estimate the true mean. We can take samples from a distribution, we can compute an empirical mean, and this theorem lets us equip this empirical mean with confidence intervals that tell us with high probability accurately bounds on the true mean. And the nice thing about these confidence intervals is they shrink quickly with the number of samples that we take. Okay, this is a useful fact, and we're going to use it. And so let me tell you the algorithm we're going to use. It's actually an extremely simple algorithm, so don't be perturbed by the notation on this slide. And it's called the upper confidence bound algorithm. And I've really already told you what it is. Let me just sort of say again what the algorithm is going to do in words, and then I'll just walk through what's written on this slide, which is really just the details of the bookkeeping. Okay. So at any given moment, this algorithm will maintain two things. For every arm, it will maintain an empirical mean. That is just the average of the rewards that we've observed for that arm so far. And it will also maintain a confidence interval around that mean. Okay. The confidence interval will have an upper edge and a lower edge. And the confidence interval will assert that with high probability, whatever the true mean is, it falls within, like between the upper bound of the confidence interval and the lower bound of the confidence interval around the empirical mean. And where do we get this confidence interval from? Well, that just comes from the Chernoff bound that we just saw. Okay. And every day, the algorithm will just pull the arm that has the highest upper confidence bound, the highest optimistic estimate for what the reward could be. Okay. And then when it pulls that arm, it observes one more reward for the arm it pulled. It observes nothing else for any of the other arms. And it just updates the information it's maintaining for the arm it pulled. It has to update its mean because it has one more sample, and it has to update its confidence interval, which is now narrower because the number of times we've pulled that arm is now larger. Okay. So that's it. Like, it's a super simple algorithm. Let me just walk you through like the notation on this slide now. Okay. So we're going to define this with. This is just the error term that comes from a Chernoff bound. Okay, like if you remember what this Chernoff bound is, it's just the square root of log of 2 over delta, our error, our sort of failure parameter delta, divided by 2 times the number of times we've pulled the arm, n. And so I just want to write that in notation here. The width of a confidence interval, if I've seen n samples from a distribution, is just this. Where here, the failure probability is set not to be delta, but to be delta divided by t, where t is the number of stages of this bandit problem. Okay, so we'll see why this is useful for us in a moment. And then we're just going to maintain empirical means and upper and lower confidence bounds for each arm. And initially, our empirical mean, we'll just initialize it to be 1/2 for every arm. We have no idea what the means of the arms are. And the way we will express that we have no idea what the means of the arms are is that our confidence intervals will initially be trivial. Meaning, for every arm, our upper confidence bound will be 1, and our lower confidence bound will be 0. This just means that we can't say anything at all about where the mean of each arm is, except that it's somewhere between 0 and 1. Okay? And we're also going to keep track of the number of times we've played each arm, the number of times we've played arm I up through and including time little t, I'll just write as NIT. And initially that's 0 for every arm. Okay. And then we're just going to repeatedly do the following. Okay, every day we'll pick an arm to play. Which arm will we pick? Well, it's just going to be the one that has the highest upper confidence bound, the highest optimistic estimate for what the mean might be. Okay, so that's just the arm I, IT, that maximizes the upper confidence bounds that we're keeping around. And we can break ties arbitrarily. So, like at day 1, all of our upper confidence bounds are 1. We can pick any arm that we want at day 1. Okay, now, after we observe the reward for the arm that we picked, we have to do some update. So we didn't observe anything at all for any of the arms that we didn't pick, and so we won't update those arms. For the arms that we did not pick, the upper confidence bound, the lower confidence bound, the number of times we played it, and the empirical mean tomorrow will be exactly the same as they were today. Those arms don't get updated at all. And for the arm that we did pick, we have to update everything appropriately. So for the arm that we picked, well, we just played the arm one more time. So we record that. We increment the counter for the number of times we've played that arm. We observed a new reward, which we have to incorporate into our empirical mean. And we need new upper and lower confidence bounds because, well, the upper and lower confidence bounds are going to be centered on our empirical mean, which has changed. And they're going to have a new width because the width of our upper and lower confidence bounds is a function of the number of times we played the arm. And we just played the arm one more time. Okay, so we recenter the confidence interval at the new empirical mean and we shrink it a little bit. Okay, and that's it. Right, so sort of, all of the notation here is just bookkeeping. All we're doing is we're maintaining empirical means for each arm and confidence intervals around those means, and every day we're picking the arm that has the highest upper confidence bound. Okay, that's it. Any questions about the algorithm? And it's called the UCB algorithm. That stands for upper confidence bound. Okay. So the UCB algorithm is a good algorithm in the sense that it obtains small regret. Okay, so let's remember, like, what might be a good regret target. Remember, like, what can the multiplicative weights algorithm do? Right, the multiplicative weights algorithm, which operates in this sort of setting with richer feedback, where every day we observe the reward of every single arm, of every single expert, it gets regret that sort of scales like the square root of the log of the number of experts times t. Okay, and that's a good bound. That's a bound that sort of, when we talk about average regret, goes to 0 at a rate of 1 over square root of t. So the claim about the UCB algorithm, which operates in this more impoverished feedback setting, we only get to observe the feedback of the arm we pulled, has the same scaling behavior in terms of t. The regret bound, just like the multiplicative weights regret bound, scales only like square root of t, and so the regret goes to 0 at the same rate, at a rate of 1 over square root of t. Now it has a much worse dependence on the number of experts. The dependence on the number of experts is now square root of the number of experts instead of square root of log of the number of experts. So the dependence on the number of experts is exponentially worse. But it's not hard to see that in this bandit setting, when we only observe the reward of the expert we pull, that's sort of necessary. You can't do better than that. And the reason is pretty simple. So, like, how big does t have to be before this bound of square root of k times t becomes non-trivial? Because remember, the regret of the algorithm, right, is never more than t, because losses are bounded between 0 and 1. So square root of k times t is bigger than t. It's sort of a trivial bound if t is less than k. Okay, the regret bound becomes non-trivial when the number of rounds exceeds the number of experts. And it's sort of not too hard to see that you couldn't hope to do better than that, because if you want to have a regret guarantee in this setting, you have to have pulled every arm at least once. If you haven't pulled each arm at least once, then it could be that the arm that you never pulled was the best arm, and you have no indication of that because you've observed nothing about that arm so far. Okay, so like, that's not true in the setting in which the polynomial weights algorithm operates. Like, we don't have to run for long enough to pull each arm at least once to get a diminishing regret bound, because, you know, even if we haven't pulled an arm, we've observed something about it. But here we don't learn anything at all about an arm until we've pulled it. And so you can't get a non-trivial regret bound until you've pulled each arm at least once. And so it's sort of necessary to have this, you know, square root of k dependence instead of this log k dependence. So this is all to say that this is still a pretty good bound. It goes, you know, it has the same square root scaling with the number of rounds of the algorithm as the polynomial weights algorithm, even though it's operating in this sort of impoverished feedback model. And it has this polynomial, this square root of k dependence on the number of experts k, but that's unavoidable in the setting in which we're operating. Okay. And so how do we prove this theorem? Oh, and note the form of the theorem, which is that our regret will be small with high probability. Okay, so we get to pick delta. And then the theorem says with high probability, with probability 1 minus delta, our regret will be small. So, you know, think about this as, you know, there's some like bad event that might happen with probability delta. The form of the proof will be to say, okay, you know, here's the bad event that might happen. If the bad event doesn't happen, then our regret will be this small, like deterministically. And the bad event, whatever it is, happens with probability at most delta. Okay. Okay, and so the bad event is going to be that basically that our confidence intervals are wrong. Okay, so like looking back, right? Like, what did the Chernoff bound tell us? Like, the Chernoff bound also had this failure probability delta. Okay, it said, like, with high probability, with probability 1 minus delta, our empirical estimate of the mean of an arm will be within this error term, within this width of the true mean of the arm, and otherwise it won't. Okay? And so the widths of the confidence intervals that we are using are the widths that come from the Chernoff bound when we set the failure probability to be delta divided by t, the length of the sequence of rewards that the algorithm is going to have to observe. And so what that means is that what the Chernoff bound tells us is that with probability 1 minus delta over t, okay, except with probability delta over t, the true mean of an arm I actually will be between the upper and the lower confidence bound that we place on it. Okay, this is just a restatement of the Chernoff bound and the fact that we were using these sort of Chernoff bound derived widths to compute the upper and lower confidence bounds. So what we know is that with probability 1 minus delta over t, the true mean of an arm I will actually correctly be sandwiched between our upper and our lower bound for it. And so that's what's true about any particular confidence interval that we write down over the course of this algorithm. Now, over the course of the run of the algorithm, we write down t distinct confidence intervals, right? Because every day we pull exactly one arm, which means we update exactly one confidence interval. Okay, so we sort of generate one confidence interval a day running this algorithm. So we generate t confidence intervals in total. And the probability that our confidence intervals fail to contain the mean for any single confidence interval is delta over t. Okay, and we only construct t of them. So that means that the probability that any of the confidence intervals fail to contain their true means is only delta. And so what we know is that with probability 1 minus delta, not just for a single arm, but simultaneously for all arms and for all days t, our confidence intervals actually correctly contain the means of the arms. Okay, and that's going to be our good event. And we're going to, for the rest of the argument, assume that this happens, and we are going to deterministically prove that the regret of the algorithm is small when this happens. And the bad event, the thing that might ruin our guarantees, is that these confidence intervals fail to correctly cover the mean. That it could be, if we get extremely unlucky, that one of our confidence intervals actually doesn't contain our true mean, that the mean is either above our upper confidence bound or below our lower confidence bound. Okay, if that happens, then all bets are off, but we know that that happens with probability only delta, and so that's how we're going to get a guarantee of the form of our theorem, that with probability 1 minus delta, our regret is small. And the structure of the argument is that, well, first, with probability 1 minus delta, all of our confidence intervals contain their true means. And then next, we're going to prove that if that's true, if all of our confidence intervals contain the means of the arms that they're intended to, then our regret is small. Okay? Does that make sense? Okay. And so that's what I want to show now. And it's actually quite simple. Okay, and so from this point onwards, I'm going to assume that the bad event hasn't happened. Okay, the bad event happens with probability delta. So now I get to assume that whenever I have an upper confidence bound and a lower confidence bound for some arm around my empirical estimate for the mean of that arm, the true unknown mean of that arm really does fall between those upper and lower bounds. Okay. So suppose that some day t, I play some action. I pulled some arm I of t. Okay. And so I get the expected reward equal to the mean of the arm that I pulled. Well, what's my regret for that day? It's the difference between the optimal expected reward, the mean of the best arm, and the mean of the arm that I actually pulled. And so I want to bound what that is. Right, so the thing that I need to argue about, the thing that I need to reason about is how much worse the mean of the arm I pulled is compared to the mean of the optimal arm. Okay, and so we can think about that. So, we don't know much, but we know one thing, right? And what's that? Well, why did I pull the arm that I did? Why did I pull arm IT? Well, I pulled it exactly because arm IT had the highest possible upper confidence bound. That's like the defining feature of our algorithm. It pulls the arm that has the highest upper confidence bounds. Okay. And remember that we also get to assume that all of our confidence intervals are correct, that all of our confidence intervals really do contain their true means. Okay. And so let me first walk through, a couple of simple algebraic observations, but then we'll conclude the same thing by me attempting to draw a picture. So, the thing we're claiming here is extremely simple. It can be observed in a simple picture that hopefully I can draw on my computer, and I'll try that in a moment. But let me first sort of walk through the simple algebra. Okay, and every step here should be sort of immediate. So on the left here is the actual average reward that I get. This is the mean of the arm that I really pulled. This is the thing that I want to compare to the mean of the optimal arm. And so what do I know about it? Well, our confidence intervals are valid, we're assuming. So the mean of the arm that I pulled is somewhere between the lower confidence bound for the arm and the upper confidence bound. In particular, the mean of the arm that I pulled, we're assuming, is bigger than the lower confidence bound for the arm that I pulled. Right? Because if it wasn't, that would mean that the bad event had happened, that our confidence intervals were invalid. Okay, well, what's the lower confidence bound? Well, the lower confidence bound is just the empirical mean of the arm that I pulled minus this width term. And the upper confidence bound for the arm that I pulled is just the empirical mean of the arm that I pulled plus this width term. And so, in fact, the lower confidence bound for the arm that I pulled is equal to the upper confidence bound for the arm that I pulled minus twice the width of the confidence bound. Okay, the gap between the upper confidence bound and the lower confidence bound is always equal to the width of the confidence, twice the width of the confidence bound. Okay. Now, I know something about the upper confidence bound for the arm that I pulled because I'm playing this upper confidence bound algorithm. So in particular, I know that this upper confidence bound was the highest among all of the upper confidence bounds of all of the arms. And in particular, it was bigger than the upper confidence bound of the optimal arm. Okay, because it was the biggest of all of the upper confidence bounds. So the upper confidence bound for the arm that I pulled is only bigger than the upper confidence bound for the optimal arm, because that's because our algorithm pulls the thing with the highest upper confidence bound. And then finally, because again we're assuming that all of the confidence intervals are valid, the upper confidence bound for the optimal arm is only an overestimate of the mean of the optimal arm. Okay, and then that's it. Because then we get to rearrange and we see that our regret at this time step is just, well, it's the difference between the mean of the optimal arm and the mean of the arm that we pulled, which we just bounded by twice the width of the arm that we pulled. Okay, so this is sort of like a little lemma that we just proved, that if I want to talk about my overall regret, right, my cumulative regret, well, of course I can decompose that as the sum of my per round regret. And what this is saying is that at any particular day t, the regret that I incur at day t can always be upper bounded by the width of the confidence interval of the arm that I pulled at day t. Okay. All right, so let me like attempt to convince you of this once again using a picture. Okay. So, yeah, so we've got the empirical estimate of the arm that I pulled. Okay, and there's the empirical estimate. We've got some upper confidence bound on that, and we've got some lower confidence bound on that. Okay, so we've got some like confidence interval here. Now, we've also got the optimal arm somewhere else. We don't know what that is, but we know some things about it. Okay, like in particular, we know that whatever its upper confidence bound is, it's only smaller than the upper confidence bound of the arm that we pulled, because we pulled the arm with the highest upper confidence bound. Okay, so, this is the empirical mean of the optimal arm, and it has its own confidence interval. Okay, and the key fact here is that the upper confidence bound of the optimal arm must be smaller than the upper confidence bound of the arm that we pulled. Okay, and now what's the worst case for regret? Right, because the worst case for regret, or our regret, is going to be the difference between the mean of the optimal arm and the mean of the arm that we pulled. So in the worst case, the mean of the optimal arm is as high as it can possibly be, consistent with the confidence interval. So in the worst case, the mean of the optimal arm is actually at the top of the confidence interval. Okay, it's like here, mu I star. And similarly, in the worst case, the mean of the arm that we pulled is as low as it can possibly be, consistent with the evidence, at the very bottom of the confidence interval. So again, in the worst case, the true mean of the arm that we pulled is down here, mu I t. And our regret is like the difference between these two things. Right, it's the difference between the mean of the arm that we pulled and the mean of the optimal arm. And what you see from the picture is that our regret cannot be larger than the confidence interval of the arm that we pulled. The length of the confidence interval of the arm that we pulled, or equivalently twice the width of the confidence interval of the arm that we pulled, is an upper bound on the regret. That's what we just proved algebraically, and what you can see from this picture. Okay, does that make sense? Okay. And so now we're almost done. So our cumulative regret is just the sum of the per round regrets. And we just proved that you can bound per round regret by twice the width of the confidence interval of the arm that you pulled at day little t. And we can rearrange that, right? So, like, suppose I pulled, arm 12 5 times. So somewhere in the sum is the width of arm 12 the first time I pulled it, the width of arm 12 the second time I pulled it, the width of arm 12 the third time I pulled it, so on and so forth. We might as well aggregate those all together. Okay, so equivalently, I can write this as, well, twice the sum over all of the arms of the width of, like arm n, or the width of arm I the first time I pulled it, plus the width of arm I the second time I pulled it, all the way up through the width of arm I the last time I pulled it. Okay, so this is just rearranging the sum. And what's the worst case this can be? Well, we know that the widths of these confidence intervals are decreasing, right? Like the confidence intervals are just shrinking at a rate of 1 over square root of n, the more times I pull the arms. And so if I want to maximize this sum, I should equalize the number of times I pulled each arm, right? Because if I'm trying to maximize the sum of the widths of the confidence intervals at the time that I pulled the arms, well, if there's some imbalance, if I've pulled arm 1 more times than I pulled arm 2, then I can increase the sum of the confidence intervals of the arms that I pulled by just sort of, doing a little bit of surgery and saying, okay, well, the last time you pulled arm 1, you should have pulled arm 2 instead, right? And because the confidence intervals correspond to these decreasing sequences of widths, that would serve to increase the sum of the widths of the confidence intervals. And so this expression is maximized when I've pulled each arm an equal number of times. And I made T pulls in total. There's K arms, so it's maximized if I pulled each arm exactly T over K times. And these confidence intervals aren't like mysterious. We have exact expressions for them. The width of the confidence interval is exactly log of 2t over delta divided by twice the number of times I pulled the arm, all under a square root. Okay, that's the width of the confidence interval. So this is like some particular sum we can evaluate. In fact, this log of 2t over delta term doesn't depend on the index of summation here, so we can bring it right outside. And the only thing we need to figure out is, what is the sum of 1 over square root of n as n ranges from 1 to t over k? And you can convince yourself, using Wolfram Alpha or a math book, that it is exactly square root of t over k. And so we've got a term that looks like square root of t over k times k, because it shows up k times in this sum. And so our overall regret is just square root of k times t times log of t over delta. Okay, so that's a proof of the regret bound for the UCB algorithm, which is this sort of purely learning theoretic statement. If we're operating in one of these sort of restricted feedback settings, online learning settings with restricted feedback that are known as Bandit problems, the UCB algorithm obtains this very nice regret bound. Okay, and now we're almost done. Because remember, at the beginning of the lecture, we set out to come up with a dynamic pricing scheme. And we're going to do that by using essentially the same reduction from pricing to learning that we used last class. But now we're going to use the UCB algorithm instead of the polynomial weights algorithm. So once again, right, we want to, we've got an algorithm that's like choosing an arm to pull every day. The thing that we want to do is come up with a dynamic pricing algorithm that chooses a price to charge every day. And so the natural thing to do is to associate prices with arms. Okay? Now there's infinitely many prices between 0 and 1. Our algorithm only works with finite sets. And so we will just naturally discretize price space. Okay, we want to consider prices between 0 and 1. So let's consider prices that are discretized at multiples of alpha. We'll have a price alpha, a price 2 alpha, a price 3 alpha, so on and so forth, all the way up to the price of 1. And there's a trade-off to manage here. Okay, so the smaller that we make alpha, the bigger the number of arms we have. And remember, we're now paying substantially for the number of arms that we have. Our regret bound depends on square root of k. So we really don't want k to be too big. And in this case, it's very easy to figure out as a function of alpha what k is, what our number of arms is. Right? It's just 1 over alpha. That's the number of points between 0 and 1 discretized at multiples of alpha. Now, we have to make sure this really fits into our setting. Okay, so we need to associate with each arm a reward distribution. And we would really like that to correspond, we would like rewards to correspond to revenue, because in the end, we want to translate our regret bound into a statement about the revenue that we make. And so what we want is that the distribution on rewards for arm P should correspond to the distribution on revenue that we get when we deploy a price P. But it does, right, in sort of a straightforward way, right? Because when we set a price P, there is a distribution over rewards that is implicitly defined by the distribution over bidder valuation functions, with some definite probability the drawn valuation of the next bidder will be above the price that we set, in which case we will realize reward equal to the price that we set, and otherwise the reward will be 0. So there's this direct translation between the value distribution and the reward distribution that we need to operate in this Bandit learning setting. And then finally, there's this sort of same observation that we made at the end of last lecture, which is that the nice thing about this discretization is that for every price P, whatever the optimal price might be, okay, like, the optimal price might not be in our discrete set, but there is some other price P prime in our discrete set that is smaller than the optimal price, but not too much smaller. Right? There's some other price P prime that's smaller than the optimal price, but is at least the optimal price minus alpha. And the nice thing about that is that we know that this price P prime will obtain revenue that is comparable to the optimal price P. Because what's our revenue? Well, it's the probability that a buyer is willing to buy the item at a price of P times the amount we charge times P. And if we lower a price, right, if we choose a price P prime that is less than P, then the probability that a buyer is willing to buy the item at that lower price has only increased, right? Because buyers only become more willing to buy the item as the price goes down. And because the price hasn't gone down too much, we can say that our expected revenue per bidder at this lower price P prime is at least our expected revenue at the optimal price minus alpha. And aggregated over n bidders, what we know is that our expected revenue at one of these discrete prices, in particular the best discrete price in this discrete set, is at least as much as the optimal expected revenue over all possible pricings, maybe minus alpha times n, because we might have lost in expectation alpha revenue per bidder, and there's n bidders. And now we can just directly plug this into the guarantees of the UCB algorithm, right? Because the UCB algorithm tells us that its aggregate reward, which in this case just translates directly into revenue, is at least as much as the reward of the best fixed arm, the best fixed price in hindsight, not amongst all possible arms, but amongst, well, not amongst all possible prices, but amongst all of the finitely many discrete prices we gave it access to, minus this regret term. But as a function of alpha, as a function of our discretization parameter, we can write this as the reward of the best fixed price in hindsight period out of all of the continuously many prices. If we're willing to lose this additional error term of alpha n, this is how much we're paying to discretize the prices. And again, we still pay for this regret term. And this is the trade-off, right? The smaller we make alpha, the less that we lose by comparing ourselves only to discretely many prices. On the other hand, the smaller we make alpha, the worse our regret term is. But alpha is just a parameter, we get to set it. And if we set it optimally to exactly balance these two error terms, then what we get is that the UCB algorithm gives us a dynamic pricing scheme that obtains revenue that is optimal, at least as good as the best fixed price, which, remember, in this digital goods setting is actually the revenue, is actually sort of the Bayesian optimal revenue we could get even amongst all possible auctions, minus an error term that grows like n to the 2/3. Okay. And remember, this is pretty good because no matter what the distribution is, okay, as the number of bidders grows large, where the bidders are drawn IID from this distribution, the optimal amount of revenue that we can make will grow linearly with n. And what that means is that if we want to think about this as a multiplicative approximation, then for sufficiently large n, we are getting a nearly perfect multiplicative approximation to the optimal revenue. Okay. So that's it. I'll see you guys next class. And I'm going to stop the recording now, but I'll stick around for a couple minutes in case there are any questions.